Hello everyone, my name is Xiangzi Liang. Today I will present the IEEE CAL 2025 paper Old is Gone, which focus on redesigning a memory allocators for single-threaded application called extramalloc, with the goal of the reducing cost and energy consumption at data center scale. And this presentation covers the research motivation, the evolution of memory allocators, the overhead of multi-threaded allocators in single-threaded scenarios, the design of extramalloc, its integration into the complementation workflow, experimental methodology, and results, and finally the future direction, Action X. The first part is background and motivation. Because applications are now multi-threaded, memory allocators are designed to handle concurrent allocations, reducing contention and improving scalability. In the 1990s, most systems were single-core, so allocators like Win32 and Dymalloc were single-threaded. As multi-threaded applications emerged, allocators evolved to multi-threaded designs. And modern memory allocators must be fast, handle different object sizes, reuse memory efficiently, and scale to many cores, which requires complex metadata. And although most allocators are designed for multi-threaded programs, many applications today are still single-threaded, such as serverless workloads, data compression, and radius. And multi-threaded allocators are complex and can hurt performance due to cache pollution. For single-threaded programs, their locks and extra metadata are unnecessary and reduce performance. If a program is known to be single-threaded, we can safely select a single-threaded memory allocator at link time. Since the threaded model can be identified during completion or linking, we revisit classic single-threaded allocators like Dymalloc, which avoid synchronization overhead, but extramalloc also adapts to modern workloads with complex allocation patterns and data behavior. So we propose extramalloc, a hybrid single-threaded allocator that adopts modern techniques on real systems. It outperforms Dymalloc and even modern allocators like Mymalloc. Although memory allocators occupy only a small portion of program code that significantly affect global performance, especially cache behavior, and are therefore considered a data center tax. Even 1% improvement can lead to substantial energy and cost savings at data center scale. Many workloads today remain single-threaded, such as serverless function, data compression, radius, and edge computing. Yet modern allocators are still primarily optimized for multi-threaded execution, introducing unnecessary overhead. This motivated us to revisit single-threaded memory allocators under modern workload characteristics. Single-threaded applications do not benefit from multi-threaded allocator design. In fact, the added metadata and synchronization effectively hurt performance mainly through cache pollution. Extramallic shows that respecializing allocators for single-threaded execution is both practical and highly effective. And next part is talk about multi-threaded allocators overhead. And multi-threaded allocator introduce two major issues. First, cache pollution, where allocators metadata if fixed application data from CPU caches. Second, synchronization overhead, such as locks and atomic operations. For single-thread programs, these costs are largely unnecessary. On the right, we can see a typical multi-threaded allocator design. Allocations first go through thread local caches and then fall back to a shared memory pool. To support this structure, allocators relied on tiered metadata and synchronization. In contrast, single-threaded allocators use a much simpler design with single-layered metadata and simplified control logic, which avoids this overhead. And modern single-threaded applications are still widely used, but they are much more complex than before, as we will see next. Modern multi-threaded allocators rely on thread local caches, shared pools, layered metadata, and synchronization. In contrast, single-threaded allocators only require a single metadata layer and simplified control logic, enabling cleaner and lower latency execution. Single-threaded design over simplicity, reliability, energy efficiency, and cost benefits. However, modern single-threaded applications exhibit more complex allocation patterns, data locality behaviors, and object size distribution. So simply reverting to legacy allocators is insufficient. Next part, I will tell the extramallic design philosophy. An extramallic follows a hybrid design philosophy. It keeps a simple single-thread architecture, but selectively incorporates proven techniques from modern allocators. Specifically, it uses a green-graded metadata and bitmap-based operation to make the common allocation path fast and close to 0.1. It also reduces overhead through the default block merging fine-grained size classes to limit fragmentation and inline functions to avoid unnecessary function call cost. The key idea is to keep what is necessary for performance while removing everything that only exists for multi-threaded scalability. The next part is talk about implementation and integration. Extramallic is designed to require zero code changes. Developers continue to use the standard malloc and free interfaces as usual. During computation or linking, the system analyzes object files to detect threaded-related function codes, such as pthread create. And if the program is identified as single-threaded, the linker automatically selects action malloc. Otherwise, the standard multi-threaded allocator is used. This allows extra malloc to integrate seamlessly into existing build workflows while remaining completely transparent to developers. Extra malloc is implemented as a real system prototype built on top of malloc. We remove threaded local caches and all synchronization mechanisms such as locks and atomic operations and replace them with a simpler single-layer metadata design. Total rate for single-threaded execution for evolution experiments are conducted on AMD EPYC 7763 platform using the SPEC CPU 2017 Integrate benchmarks with 64 copies. We compare extra malloc against classic single-threaded allocators, dymalloc, as well as modern multi-threaded allocators, including jamalloc, tagmalloc, and mymalloc. This setup allows us to very evaluate how allocator design choices impact performance in allocator-intensive single-threaded workloads. And next part is talk about performance and evolution. And overall, extra malloc achieves 1.19 geometric mean speed up over dymalloc and 1.03 speed up over mymalloc on SPEC CPU 2017 Integrate benchmarks. While the average improvement may appear moderate, it is important to note that most SPEC CPU benchmarks perform relatively few dynamic memory allocators during steady execution. As a result, allocators optimizations have limited impact on many compute dominant workloads. However, for allocation-intensive applications such as XLMA Bank, extra malloc provides significantly larger performance gains, up to 1.13 over jamalloc and 1.19 over mymalloc. This workload involves frequent allocation with diverse object size, making it highly sensitive to allocation overhead. These results indicate that extra malloc effectively target allocation overhead and is particularly well suited for real-world data-centric applications that exhibit complex and substantial allocation patterns rather than purely compute-bound benchmarks. And further analysis of uh, Kalesnikbeck shows that extramollic significantly reduces both L1 and L2 cache MPKI. This improvement mainly stem from a simplified single-layer metadata design, which reduces cache pollution and eliminated synchronization overhead, thereby accurating common allocation paths. And next part is talk about future work Action X family. And beyond memory allocations, the others propose Action X, which extends the same design philosophy to other system libraries such as networking, file I/O, and logging. Since these components account for a substantial portion of data center overhead, even modest performance improvements can translate into significantly energy saving at scale. And revised conclusion script. In conclusion, modern allocators are over-designed for multi-threaded workloads. When applied to single-threaded applications, their complex metadata and synchronization introduce avoidable overhead. Extramallic demonstrates that by revisiting a single-threaded design philosophy and selectively incorporating key technicals from modern allocators, it is possible to achieve consistent and measurable performance improvements, as evidenced by the SPEC CPU 2017 results. More importantly, this work highlights a broader insight. Designs optimized for concurrency are not always optimized for all workloads. Building on this observation, we propose the ActionX framework, which opens new research direction by extending these principles beyond memory allocation to other system libraries, which with the potential for significant performance, energy, and cost benefit at data center scale. And thank you, everyone.